Hello everyone and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinions and teaching on research appraisal and methodology. My name is Gio Perrin, and together with Professor Sababala Subramanian, Adam Haig, Ben Wood and Josh Lau, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber.
So, descriptive statistics, that's what we are doing. We've done a couple of lectures and called them parts 1 and 2. So, we're in the final stretch of descriptive statistics, right? So, what have we learned so far? In the first two lectures, we discussed a few things. So, if you haven't, if you weren't at the last lectures, so you could go and look them up. So we talked about data types, we talked about normal distribution, we talked about parameters that we use to describe data, which is based on the type of the data and whether the data is normally distributed or not, right? So here's this figure that I've shown on a couple of occasions on the different ways in which data can be classified. I find this a very useful figure to refer to from time to time, and whenever I have to do descriptive statistics or I have to think about a statistical test to use. So again, very quickly, you can classify data as categorical or measurement or scale. You can classify categorical data as qualitative or semi-quantitative, and measurement or scale data is also called quantitative data. Using another kind of classification, we can split data into nominal data, ordinal data, interval data, and ratio data, right? So I'm going to leave you to go back to those other presentations and have a look at it again if you are not able to remember the differences between these different types of data. I'm going to move on. We talked about data distribution. If it is quantitative data, we talked about the need to try and differentiate this into normal data or data that is normally distributed and data that is not normally distributed. And we talked about the various parameters that can be used to describe data based on the type and distribution. For example, we said normally distributed continuous data should be described using mean and standard deviation, while continuous data that is not normally distributed should be described using the parameters such as median and range. Okay. We talked about graphs and tables in part 2 of our descriptive statistics series. We discussed when to use which graphs and which tables. We talked about a few common mistakes, and I gave you a few tips. Now, what we'll do is just summarize this again using an example. So I'll highlight the different ways to describe a single data set, and let's start off with an example, and let's consider a scenario where we want to evaluate the relationship between BMI, body mass index, and postoperative pain scores, let's say pain in the first 24 hours in a cohort of patients undergoing a specific operation, right? So if you're doing this kind of study and you're collecting data, you might have data on a spreadsheet that lists the BMI of the patients and lists the pain scores on day 1. So you've got big, long columns going down up to 100 rows and showing the BMI and the pain scores for these patients, right? And if you're just wanting to describe it, obviously it is cumbersome and complicated and not feasible to present your whole Excel sheet in the document or the report that you're writing. One way of doing it is by means of a bar chart. So we talked about bar charts. And in a bar chart, you might want to categorize BMI into 3, 4, or 5 different categories. And here you've got healthy, overweight or obese, and then moderately obese. And you've got the median pain scores that are depicted in the y-axis. So this is a simple way of describing the BMI, the pain scores, and the relationship between these two variables. But there are some problems. Obviously, and categorizing them as healthy or overweight, obese, or morbidly obese can be problematic. The readers may or may not accept your definitions, your categories, and also you lose a lot of useful information by just depicting median pain scores, right? Let's think of another way of doing this. So let's say you want to categorize pain scores as well, and as per the severity of pain. So maybe 1 is very minimal pain, 2 is moderate pain, and 3 is severe pain. And you've got your categories of obesity or BMI, and you are plotting or depicting the relationship between BMI and pain in terms of the categories. Okay. Again, this might be a useful, visually attractive way of doing it, but the problem is that your categorization is artificial, and then you're not really depicting or giving the reader the full picture of the scores. Right, how can we do this? How about a box and whisker? So we talked about box and whisker plots as well in part 2. So you've got your healthy and overweight, obese, and morbidly obese categories, the 3 categories of BMI, and you're plotting median and interquartile range with regard to pain scores in each of these 3 categories. So in comparison to the bar charts, you're giving a bit more detail, but again, categorization is a problem because it's arbitrary, as we discussed. Line charts show the same scores as the bar chart, just as a line going across the 3 groups. You often see this kind of representation in some surgical journals. This line chart should not be used for this kind of categorization or this kind of description. They should be reserved for scenarios where you're looking at trends over time. So line chart should typically be used in scenarios where you're looking at trends over a period of time. Okay, so it can be done, but it's not ideal. How about a table? In the table, you can have your categories along one of the columns, and then you can present the median of the range if it's not normally distributed data, or you can present mean and standard deviation if it's normally distributed data. So lots of numbers, so this is valid. The downside of this is that it is not visually representative. You don't really get a picture in your mind as to the relationship between these 2 variables. Okay, so there are a number of ways of doing it, and each of these ways has their own sort of advantages and disadvantages. The thing to do, which would be considered most optimal in depicting the relationship between these 2 sets of these 2 variables, which is BMI and pain, and both of them are continuous variables, is what we call a scatter plot. Right? So in the scatter plot, as you see here, you've got the BMI on the x-axis, you've got the pain score on the y-axis, and you simply depicted every in the study, the 100 patients, as a little dot, which represents the relationship between the BMI and the pain score. Right? So it's visual. It depicts a relationship very clearly. There are no artificial categories, and it can show up a number of awkward or odd findings. For example, you find that the people don't seem to have much pain at all. Sorry, there are no patients with very low pain scores, which is slightly odd. And also you find here that there are a number of patients who have a BMI of exactly 50, and you don't seem to have people with a BMI of more than 50. And that could be an artifact. Maybe there's a problem with the scales. The things to avoid in a scatter plot is a line. You sometimes find that people draw what they call a regression line across a scatter plot. And if the idea is to simply show the relationship between variables and not try and predict one variable from another, and obviously you're not going to try and predict pain scores from BMI and vice versa, then a regression line should not be drawn. Okay, and the other mistake that sometimes happens is that people try and join the dots in a scatter plot. And again, you shouldn't really join the dots because that really doesn't give you any extra meaning and might simply confuse the interpretation. Okay. There's some background noise. I don't know if people need to mute their microphones. Right. Now what we're going to discuss is a special type of table called the contingency table. So what is this? It's also called the crosstabs or cross-tabulation, and simply it is just a special type of frequency distribution table. It's often used in biomedical research, and basically it shows the relative distribution of two categorical variables. So these two words are important. The distribution of two variables relative to each other, and they're usually categorical, although sometimes you can have ordinal variables as well. So here's the contingency table. So what are the two variables? The first variable here is a test variable. So is the test positive or negative? So it's a binary variable. And the second variable is here in this example is a disease variable or the disease status variable. So is a disease present or absent? And then you've got these cells which ought to be mutually exclusive. So there are 4 cells here because for each variable you've got 2 options. So 2 times 2 is 4. And then you have the totals represented as either column totals or row totals. Okay, and I'll explain this in a minute, but in a contingency table, ideally you ought to present either the column totals or the row totals, not both. Right. So you've got the same kind of contingency table presented in 2 different ways. The first one on the left is with row totals, and the second one on the right is with column totals. Okay. Now, usually, or as a convention, we tend to present outcomes as columns. So outcomes in column headings. And this could be either outcomes following an intervention as an example, dead or alive, or recurrence or no recurrence, or the occurrence of disease after exposure to the risk factor. Those are outcomes, and by convention, they are presented as columns. And the risk factor of the intervention is usually presented as rows. I mean, you could do it the other way around, but if you follow a convention, then it's easier for readers to follow and interpret the data in the contingency table. Right? The next thing, thing to keep in mind is that when you're presenting totals and percentages, so on the left-hand side you have row percentages and row totals, and on the right side you have column percentages and column totals. Which ones to present really depends on how the study was designed. So what do I mean when I say this? So if you have a case control study, and if you remember from our previous lectures on case control study, you may remember that you start off with people with the disease and people without the disease and go back and look to see if they had the risk factor or the positive or negative test. So it is clearly retrospective. You start off with the outcomes, and therefore you should be presenting column totals and column percentages. On the other hand, if you are doing a cohort study, or if you're critiquing a cohort study, in a cohort study, you start off with the risk factor of the intervention, you follow people over a period of time to see if the outcome has occurred or not, and therefore, because you're starting off with the risk factor or the intervention, over time, you should present row totals and row percentages. Okay, so I hope this makes some sense. If not, just have a look at the talk on case control and cohort study designs, and then come back to this, and I'm sure that will be it'll be clearer for you. Right. So, what's the value of a contingency table? And the obvious value is that it shows the relationship between variables. You look at the table, and then you get some idea as to the relationship between the disease and the test. It helps you calculate parameters that assess association. So the common measures of association are the odds ratio and the relative risk, where we have discussed this before in one of our previous talks. So you can look that up. And there are some other uncommon measures of association that I wouldn't worry too much about because they're not very commonly used in surgical research. And the next thing it helps you do is it helps you determine statistical significance of the association that you worked out. So if you've got an odds ratio of 3, and then you have to do a test to determine if that odds ratio of 3 is statistically significant in this study. And we're not going to discuss statistical significance because that is inferential statistics, and we're talking about descriptive statistics. Okay, so we'll go on. And there are some other related tables called, a typical example is the pivot table. Excel does it for you. Pivot tables you might have heard of. It is very different to the contingency table. In a pivot table, you get aggregates, right? And not counts. Okay, so aggregates are summated measures, so they're very different and shouldn't be confused with the contingency table. All right, so much for a contingency table. Oh, there's another slide. So yeah, there's one other slide. So in a contingency table, in the tables that we've seen, you've got 2 variables which have, each of which has 2 levels. But sometimes you can have 3 levels in one or more variables. So if you have 3 levels, that becomes a 3 by 3 table. If you have 2 levels in one variable and 3 in another, that's a 2 by 3 table, and so on. So it doesn't always have to be a 2 by 2 table. That's something you need to keep in mind. Okay. Another mistake that I notice fairly commonly when I review papers is that people insert additional columns or rows for missing data, like this. So in this table, you find that if you look at the column headings, you've got disease present as one heading, you've got disease absent as another heading, and then you've got unknown status as a third heading, right? And you will find that there are very few patients where the disease status is not known for a variety of reasons, and the authors have inserted yet another column and added the number of unknowns. I mean, they might assume that they're being open and transparent, and that's very good. But having a separate column for unknown status just distorts the relationship between the outcome and the risk factor. So it is to be avoided. And what we usually advise is that you remove the unknowns from your denominator and simply present the patients for which both the disease status and the test status is known. And you can clarify that in your method section or your limitation section and say that you've excluded X number of patients, 11 in this example, from the calculations, from further analysis, simply because the disease status was not known. All right, so now we're moving on. So we're going to talk about the forest plot. I think a number of you might have heard of the forest plot. We've certainly listened to a paper with lots of forest plots in it. So what is a forest plot? So a forest plot is a plot used to compare a specific outcome in 2 different groups reported by a number of similar studies, and is usually done as part of a meta-analysis. So the outcomes, a specific outcome, which could either be occurrence of the disease, if you're looking at a risk factor or a diagnostic test, or the effects of interventions, if you're looking at patient being alive or dead after different types of treatment for a specific cancer, for example. You might be looking at recurrence of a disease. You might be looking at hospital stay. It could be any outcomes following different interventions. Groups, and the groups are usually stratified by the risk factor or by the intervention. And the studies could either be randomized controlled trials or observational studies, and ideally not a mixture of randomized controlled trials and observational studies, as we discussed previously. Right, so here is an example of a forest plot. This is from a systematic review done by one of our students in Sheffield on hypocalcemia after thyroid surgery. So let's divide this forest plot into its various constituents and go through them. Right. Firstly, in a forest plot, you want to mention or cite the various studies that you've included in the forest plot. So you usually put them in chronological order, and that's not mandatory, but most people tend to do it, and they list the studies in the order in which they were published. So the oldest studies first, and the most recent studies right at the end. Okay, so you're simply listing the studies. That's all you're doing there. Next step is you're telling us what the numbers are in the different groups, in the 2 different groups, in each study and what events were in the different groups. So here you have hypocalcemia as the event or the complication in patients with Graves' disease and patients without Graves' disease. And you're effectively comparing hypercalcemia rates in these two groups of patients. So for each of the study, you've got some Graves and some non-Graves patients, and you're just writing down the numbers of patients with the complication in both these groups. Okay. Then you have a column that talks of the effect size or the measure that you're interested in. In this example, the odds ratio. The odds ratio that looks at the association between hypocalcemia and the type of thyroid disease. And finally, you've got the plot, the forest plot. Okay, so we'll just explore the plot and look at it in a bit more detail. So this is the plot. So what does this show? So it shows a number of squares, each square specific for each study included in your meta-analysis, right? And the squares, the size of the squares reflect the effect size and the weight. So where the square is, that gives you an idea of the effect size. So the first square, for example, if you go down onto the x-axis, it points to an effect size of about 1.3 or 1.4, which is the odds ratio in this particular example. Now, because the square is small, it probably reflects that reflects the sample size. The sample size is probably small. Okay, so that's what the squares represent. The lines on either side of the square, or the whiskers, the horizontal lines that you see here, give you the 95% confidence interval around the effect size. Okay. Now the diamond here, low down, gives you the summated effect size. Takes into account all of these four effect size from these four studies, and it gives you the aggregate. Right. Now, there's a vertical solid line, which is here, which you can see here. This is the line of no effect. So the odds ratio or relative risk, which are both ratios, the line of no effect will be 1, which means that in both the intervention groups and the non-intervention groups, the complication rate is the same, or the outcome is the same, right? So that's the vertical solid line, which is a line of no effect. Now, I've just drawn a dotted red line, which passes through the middle of the diamond. So the dotted red line, vertical dotted line, shows the summated effect, summated measure that you get by doing the meta-analysis, which is the aggregate of all of these four studies. So it usually passes through the middle of the diamond, the black diamond. And the edges of the diamond, as marked here, and gives you the 95% confidence interval of the summated measure. And what you should be looking for is whether the edges of the diamond overlap the line of no effect, which is the vertical solid line. And here it does not overlap the line of no effect. And that means that's a significant result. So you've got the odds ratio of almost 1.8, which is a summated odds ratio for this meta-analysis, with 95% confidence intervals of around 1.5 to 2.3. And that 95% confidence interval does not include the odds ratio of 1, which is a line of no effect, and therefore this is a significant result. The summated measure, the summated odds ratio in this meta-analysis is significant. Okay, so I hope that makes some sense. Now, this effect size or measure can either be a ratio, for example, odds ratio or relative risk or attributable risk, or it can simply be a difference. For example, you're looking at difference between difference in length of stay in Graves' disease and non-Graves' disease patients undergoing thyroidectomy. So there you have a difference. It's not a ratio, right? And the SMD refers to standardized mean difference between the groups. So if you have a standardized mean difference, the SMD, then if there's no difference between the groups, then the line of no effect should be 0, right? If you have an effect size which is a ratio, i.e. odds ratio or relative risk, then the line of no effect would be 1, because that's what ratio means. If the ratio is 1, that means there's no difference. So I hope that makes sense. So you've got to keep in mind that the line of no effect should be at 1 if it's a ratio, for example, odds ratio or relative risk, but it should be at 0 if you're looking at difference between groups. So when you look at a forest plot like this, there are two key questions you want to answer. One is, what is the summated measure? So in this case, it is 1.8. And does the 95% confidence intervals or the edges of the diamond overlap the line of no effect? So those are the two key questions you want to try and answer when you're looking at a forest plot. The forest plot also demonstrates heterogeneity, statistical heterogeneity. In other words, how different are the results of studies to each other? So they're all on one side of the line of no effect, and in this case, all these squares are on the right side of the line of no effect, or are they a bit scattered, and are the odds ratios relatively similar or very different? So that gives you a visual understanding of the statistical heterogeneity of the different studies in the meta-analysis. Right, so we've done forest plot. The last plot we're going to discuss today is the funnel plot. Right, so what's the problem? Why do you need this plot? Now, meta-analysis generally uses published data, usually. You don't find authors of meta-analysis and systematic reviews trying to get hold of non-published data to include in their meta-analysis, right? And we all know that a number of studies may just not be published for whatever reason. There are numerous reasons for that. And it is quite possible that there are some differences, some underlying systematic differences between data that is published and data that is not published. Okay, so that is a problem. Now, what this can result in is what we call publication bias, which means that it is possible that the summary measure of your meta-analysis may not really be the true effect, because there are some important studies that are not being published and that deviate or pull you away from the truth. And they could be because the publication getting delayed. There are some big studies coming out, and it may come out in print just months after you've published your meta-analysis. That could be a reason. It could be that the same study has resulted in numerous publications, and you've included the same set of data over and over again. It could be because there is language bias or citation bias. It could be because negative results or studies that do not show difference between interventions just don't get published, because journals and editors and reviewers are just not interested in negative results. That's another problem. That's another common problem. Right. So one way in which you get to assess publication bias is by plotting a funnel plot. Right. So we've understood how a funnel plot may be useful. So let's look at the constituents of a funnel plot. So this is a good example of a funnel plot. I've taken this from a free available paper in the BMJ. So what does this show? So it shows a number of blue dots, right? Blue dots covered by a black circle, and each of these dots represents a single paper. So the number of papers in this meta-analysis, and each paper is represented by a blue dot or a circle. Now on the x-axis, you have the effect size. This effect size, like I said before, could be an odds ratio, could be relative risk, could be standardized mean difference, and so on, right? And because it's a ratio, in this particular example, they've represented this on a logarithmic scale, as ratios usually are. On the y-axis, here in this example, you've got standard error, but you could also have what we call sample size. So effectively, what you're doing is you're comparing the odds ratio in these various studies to their standard error here. Okay, so you're comparing, you're plotting the relationship between two quantitative variables. So in other words, this is essentially a scatter plot, the funnel plot, right? So what about this triangle, the dotted triangle? Now, the dotted triangle is a triangle that you calculate or work out using the software, and this represents the area in which 95% of these studies should lie when you plot them on the basis of their odds ratio and their standard error. Now, the vertical dotted line is the summary measure of the meta-analysis, just like we discussed with the forest plot, right? So here it's around 0.5 or so. And the solid vertical line is a line of no effect. And like I said before, it should be at 1 because it's a ratio. So for odds ratios and relative risk, the line of no effect should be 1. Okay? So in in this funnel plot, all of these studies are within the dotted triangle. And these studies are fairly symmetrically placed around the summary measure or the dotted vertical one. Okay, so that's what you're looking for symmetry around the summary measure. And it is fairly symmetrical. Okay, right, so you look for symmetry around the vertical dotted line. And if there is asymmetry, then there could be a problem. Now, that problem may be publication bias, but there are lots of other reasons for asymmetry. So just because you have asymmetry in the funnel plot doesn't mean there's publication bias. It could be publication bias. It could be significant heterogeneity between studies, in which case you shouldn't really have.
Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical podcast.